Good evening, ladies and gentlemen. Welcome to lesson 4 of the special relativity topic. Today we're going to talk about time dilation. Now, having a look through the syllabus, there are 4 or so separate objectives that we need to consider, and a lot of them involve both stuff involving time dilation, length contraction, and relativistic momentum. So some of these you're going to see pop up in the next couple as well, just with the terminology changed a little bit. So our first one here is recall the consequences of the constant speed of light in a vacuum. In this case, one of the things you need to recall is time dilation, the other being length contraction. We need to define the following terms: time dilation, proper time interval, and relativistic time interval. So here, and here. I do apologise, my handwriting is never great. Describe the phenomena. Down here. Describe the phenomena of time dilation, including experimental evidence. So that's important. And then solve problems involving time dilation. So using a little bit of math there. So let's get into this. So far we've talked about a classical relativity in the idea that we have reference frames that are important. We have the idea of simultaneity, that something that is simultaneous for one person might not necessarily be simultaneous for another observer. And finally, we discussed relative motion a little bit. Now, the text has a pretty decent explanation of the light clock thought experiment, the Gedanken, to show the idea that time is not the same for moving objects that it is for stationary observers. I'm going to go through it really briefly here. So let's draw 2 situations here. We have a person who is sitting on a bus. Let's draw a seat, or a person, and he's sitting there, and he observes a beam of light going from the floor up to the roof, hitting the roof, and then coming back again. So to him, the light is just moving up and down. Now, according to our principles of special relativity, firstly, that the laws of physics are the same in all reference frames, and that the speed of light is a constant. Then, if we think about this, light is moving at the speed equals c. We don't know what the distance is, but this person could time how long it goes and say that time equals t naught. And we're going to call t naught here the proper time interval. Proper time. And that's because the observer who is observing this is in the same reference frame as the thing, is the same reference frame as the light, or the thing that is going to be in motion in a second. And so if we were to work this out, we could go, well, velocity equals distance over time, so the distance that the object moves here going up and down must equal c times t naught. That's fairly straightforward. Some people will say, well, if the time is all the way up and then all the way down, d would be c times t naught over 2. That's how Walding does it in his text. However, you'll see that the divide by 2 cancels after the first step of math anyway, so it doesn't really matter. So here's observer 1. Now, this must be true. There is no reference frame that is more valid. There's nothing in here that we've done that is weird, and you could experimentally prove this to yourself. Now, you can't do it with light too easily, but if you go and pop on a train or a bus that's moving at constant speed, and you throw a ball up and down, you'll see that it will go up and go down relative to you and not move forwards or backwards inside the bus. Like, you don't throw the ball up and it suddenly goes racing to the back of the bus and smacks some poor person in the face. It just goes up and down. So this is our person on the bus. Let's go person off the bus. Okay, so the bus is moving. So here we have our bus. It is moving with velocity v. Here we have our person. Here's my chair. Here's my person sitting on the chair. And here we have an observer outside. Now, the light will go up and down inside the bus. However, this bus is going to move. So this person here will see that this light goes from here up to the roof and then back down again. Now let's think about the time it takes for it to do this. We know this distance from here to here, we already have from our previous little bit of math here. But what about this distance here to here? Okay, so in the time it goes from this point to this point is going to be t. In this case it would be some t value that we don't actually quite know what it is, but it's also going to be the same time it takes for the light to go from here to here. So we're going to call this t our relativistic oops, that's a very weird looking S, time. And that's because this person is moving relative, well, this light here is moving relative to our observer. Okay, the observer is standing still and the light is moving relative to it. Now this distance from here to here, we don't know what that is. Let's give it a length L. But what we do know is that the bus will travel this distance in that time, so L will equal V times T. Now here's the really confusing part. Light travels at the same velocity no matter what reference frame you're in. So even though to this person inside light is moving up and down at this value, we can see, well, it's not moving just up and down, it's moving all the way over there. That's a lot further, isn't it? But it's still moving at the same speed. Can't change. That's a bit of an issue. Let's give this the symbol D for a second. We also know that D will equal C times T, because the light will go from here all the way up to here in the same time that this person out here sees, and it will go at the speed of light. But there's a bit of an issue, because now if we were to think about this, well, it's going up and down, but it's also going left and right. Well, if we were to add these velocities together, surely it must be going faster now, but it can't. The velocity of the speed of light is always the same. Now, if you chuck these together, we would get L squared equals D squared plus, oh, sorry, can't do my Pythagoras, D squared, little d squared, equals L squared plus D squared. And if we substitute those in, CT all squared equals VT all squared plus CT naught all squared, and you can do some rearranging, and the textbook shows the rearranging for this, so feel free to do that. Have a look at that in your own time. You don't need to be able to prove the rearranging. You should be able to sort of do this step. This is fairly useful, and show this bit, but then if you go, ooh, magic hand waving math, T equals T naught divided by the square root of 1 minus V squared over C squared. And remember, this formula is inside your formula booklet on any of your exams. Well, you can't really say that you don't understand it, because you're not getting marked on your ability to rearrange an equation. There is nothing in that syllabus, the objectives that we went through at the start of the lesson, that says that you need to be able to prove this. You just need to be able to explain the consequence of it. Okay, so that's what we're doing here. This formula tells us that to this person on the outside here, they are going to see this take a different amount of time. Because the velocity doesn't change and the distance is longer, so let's write that formula for a second, D equals CT, this is fixed. We can't change that. So if this has increased, this must decrease, because our constant here is still the same. Okay? Sorry, big mistake there. If that has increased, that has increased, because our constant cannot change. Okay? If it is going a further distance, then the time it takes must be longer, and so there is a time dilation effect happening here. Okay, so time dilation is this result of the theory of relativity, and is the idea that for an object that is moving, okay, it experiences time slow, or for someone observing something moving, time is moving slower for the observer than it is for the thing inside of it. Okay, to dilate means for it to expand. So let's have a look back through these things here. We've got call the consequences. That's the first consequence. Time dilation. Time expands. Define the terms. We've defined those. Remember, you do have a glossary at the back of your textbook, so make sure to use those. And describe the phenomena, including experimental evidence. So let's talk about some evidence. We talked about muons earlier on, that the amount of muons reaching the surface of the Earth, and this is in chapter 9.1 of your text, is too high. They live on average 2.2 microseconds. And even moving at near the speed of light, they go to about 99.99% of the speed of light, they don't actually hit the surface of the Earth. They shouldn't hit the surface of the Earth. They should just run out. Their length of time, their length of life, it should just basically make them run decay way too fast. But they don't. There is a significant amount of them hitting the surface that they are very easily detectable with a muon detector. One of my goals is to build a cloud chamber for the school, because we just need a bit of dry ice and evaporated alcohol in a dark room, and we'll be able to detect these ourselves. They are that easy. We could do it with some basic stuff in the lab. So muons are experimental evidence to show that yes, there is that there is some effect happening here. Now, time dilation is not the only part of it. There's also length contraction, which will be coming up in the next couple of lessons. However, I'd recommend going back to chapter 9.1 to look over muons again, now that you're starting to see this idea of time dilation. And I'd also recommend having a look at what's what I'm looking for, some of the videos that I've been linking on the eLearn, because they explain muons and time dilation a lot better than anything I can really do, and giving lovely pretty pictures as well to help wrap your head around it. Now, I am going to do one quick example using this equation, because you're going to need to. The hardest part for any question that you'll read on this is whether something is going to be t or t naught, in that whether you're being told the relativistic time or you're being told the proper time. We're going to use muons for a second, and I just said a second ago that muons have a life of, or an average life, or a mean life of 2.2 times 10 to the negative 6 seconds, 2.2 microseconds. And they have a velocity of about 99.99% of c, the speed of light. Generally, this is written as 0.9999 c. So the question is this average life a proper time or a relativistic time? It is the proper time. Okay, the muons are the thing that is moving, so it's proper time. That's how long it would live if it was sitting still in our reference frame, and it still lives 2.2 microseconds. We just see it living a lot longer because it's moving for a lot longer. Oh, because it's moving so fast. So let's substitute these things into this equation. Now I'm going to leave velocity as this, and you'll see why in a second, because it will make some of this math a little bit simpler. So t equals t naught, square root 1 minus v squared over c squared. So t naught is equal to 2.2 times 10 to the negative 6 divided by square root 1 minus 0.9999 c squared over c squared. And what's really great here is the c squared and the c squared that's about to propagate here will cancel. So now I will just have equals 2.2 times 10 to the negative 6 square root 1 minus 0.9999 squared. Really useful to recognize that. Now, someone's stolen my calculator. Let's load one up on the computer then. So, 0.9999 squared minus 0.9998, and I want the square root of that, and then I want to do that's weird. What do I do there? times 10 to the power of negative 6. There it is. Divided by 0.0141417. That should be enough precision. Gives us a new time of 1.55 times 10 to the negative 4 seconds. You might go, that's really small. I mean, that's one less than 1 millisecond, and it's very, very small to us anyway. But at the speed of light, you can still go a fair amount of distance in 1.55 milliseconds. It's nearly 100 times larger than what happened before. So we're saying that because it's going at 99.99% of the speed of light, that its time that we see it going for is 100 times longer. Now, even with this time, it's still not going to get through the hundreds of kilometres of the atmosphere. There's another thing at play there, and we will talk about that when we deal with length contraction next, but this is experimental evidence that shows us that the theory of special relativity and the two consequences of it, time dilation and length contraction, must be true. Now, it could be that there's a better theory for us down the track, but we're not at that point, we haven't found it, and so this is the one we take as the moment of being the thing that is true. Okay, I would definitely have a chat about proper time and relativistic time, so I just want to go through that really quickly. Proper versus relativistic, and you can kind of think of it as which is the moving and which is the sometimes relativistic will also be called dilated time, by the way, which is the moving and which is the stationary clock. And then you can go, well, where the clock's involved, and you can think of it instead of moving versus stationary clocking, and moving versus stationary observer. If, let's say that we're travelling on a trip from Brisbane to Sydney, that's a long way, you can't see when I get there, so for you would need two things to record the timing of me leaving Brisbane and getting to Sydney. You would need a timing device here to start the time. It might be that you use a laser line to say, oh yeah, you cut the laser line, here's the starting time, or visual observation, and then you'd have something similar in Sydney to see when I get there. But for me, I could record how long it takes to get to Sydney with one clock. I'd only need one object to record it because I would be with it travelling the whole way. So proper always is the moving thing, or the one clock, while relativistic is still. It needs two clocks. The thing that sort of confuses students sometimes, if we go back to this previous example with the bus, you can go, but I could record how long it took to get there. No, you couldn't, because here's the thing, if you saw it got there, by the time you have hit stop, it has travelled further because the light takes time to travel back to you. You'd have to have some person here and some person here, that when everything is synchronised, this person goes, oh yeah, passed me at 10 o'clock. This person goes, oh yeah, passed me at 10:01. While the person on the bus would be, oh yeah, started at 10, ended at 10:00 and 50 seconds. Okay, so these are, it's a very tricky thing, and the only way really to get your head wrapped around it is to read as many questions as you possibly can and have a go with doing things. Now, there's a couple of mathematical shorthands mentioned in the text as well. The Lorentz factor is something that's useful. It's not part of your syllabus, but it is something that might be useful, especially if you're going to do a special relativity research question. So have a look at that. And Table 1 there has a fairly interesting table about the time dilation effects of different speeds, moving all the way up to some very, very fast electrons, things that we'd be using in like the Higgs boson, in the Large Hadron Collider and that sort of research. Alright, so we've gone through a couple of things today. We've talked about time dilation, we have looked at the consequences of the speed of light, 3 new terminologies, make sure you can remember those. We've seen an example of how to solve problems using the time dilation equation. Thanks very much for listening. Have a great evening.